Welcome to homework.
So there are two ways to solve this problem. One is using energy conservation and the other is using Newton's second law. So we'll be using Newton's second law to solve it. So we have a crate which is on a plane. So let's draw the figure first. So this is the plane where the crate is lying. So the red box over here is the crate. Now what we need to do here is first draw a free body diagram of the system, and then we can think about how to solve it using Newton's second law. So let's first choose the axis according to our convenience. Now what we're doing here is we're choosing x as the parallel to the parallel to the plane, and the vertical direction is basically perpendicular to the plane. Now this is angle theta. So first of all, due to the weight, we have mg acting downwards. So it has two components. One is parallel to y-axis, which is mg cosine theta. And then we have parallel to x-axis, which is mg sine theta. Also, since the crate is going down, that's why the friction is acting on the opposite direction. We call it F sub R. And then, of course, we have the normal force which is acting on the crate. That should be perpendicular to the plane. We call it Fn. Now, if we apply Newton's second law on y-axis, we'll see that there is no movement in that direction in y-axis. So all we have is Fy, which is equal to the normal force minus mg cosine theta. Now the reason this whole thing is zero because there's no movement in y-axis. Now what we did here is we took upward direction as positive y, so that's why mg cosine theta became negative. Similarly, we'll consider positive x as downward direction. So if we do so, we'll have fx, which is equal to mg sine theta minus f sub fr. That should be equal to m times a, because the whole system or the whole crate is going down with an acceleration a. Now, since since the crate is moving, so we have kinetic friction, or we have the coefficient that we'll be using is coefficient of kinetic friction. So from equation, we know that F of Fr, which is a frictional force, is equal to mu k, or coefficient of kinetic friction, times F of n, where F of n is the normal force. And we can get that from this equation right here. So Fn is equal to mg cosine theta. So we can put that here to get the force. Now, let's actually combine all this together and see what we get for fx. So here we'll get ma, which is equal to mg sine theta, minus mu times fn, where fn is mg cosine theta. So we'll have mu k mg cosine theta. From here we can get rid of the m's. So finally we'll have a, which is equal to g sine theta minus mu k g cosine theta. Now if we use the given values, we see that we can actually take g outside, and we'll get g times sine theta minus mu k cosine theta. So for the given value of g, it's 9.8 meter per second squared. Then sine theta is sine 25 degrees because theta is given as 25. Then for coefficient of kinetic friction, it's 0.19, then cosine 25 degrees. And combining all of them together, we see that the velocity is 2.454 meter per second squared. Sorry, the acceleration is 2.454 meter per second squared. So that's part A, where we had to find the acceleration. Now in part B, we have to find the final velocity when the crate reaches the bottom of the incline. Now for that, we can use equation 2.12c, which gives us v squared minus v naught squared equals to 2a x minus x naught, where v naught is the initial velocity and v is the final velocity, and x minus x naught is the displacement. So in our case, our initial velocity is 0 because the crate starts from rest, so we can put that 0. So what we have now is v equals to square root of 2a x minus x naught, where we've already calculated a from the previous part. So if we use the given numbers, we see that a is 2.454 meter per second squared, and the displacement is basically from where the crate starts to go down, which is 8.15 meters. Combining everything together, we see that velocity is 6.3 meter per second. Thank you.